Hello, class. This will be the recorded lecture for section 6.3 in our book, and this talks about exponential functions. And so what we're going to start with is the introduction and some attributes and show you a graph or two of an exponential function. So first of all, the definition. So the definition of an exponential function is defined at, say, y equals a to the x. And now we have our variable up in the exponent. And so that's what we mean by exponential. And so the a is defined as the base of the exponential function. And the idea is, let's pick, well, a equals 1 is kind of a boring exponential function, right? So let's just look at that. That would be a nice way to start, but it doesn't matter what x is, right? 1 squared is 1, 1 cubed is 1, etc., etc. So a base of 1 is kind of boring. So let's start with, say, the base of 2. And let's do a quick graph of this and kind of see a couple of the attributes. So say like we have 2 to the x. And let's do a little sketch over here. And so the idea is let's plug in some numbers, see what we get, right? So this would be x, this would be y. And so if we plug in 0, 2 to the 0 power by definition is 1. And so we plug in 1, 2 to the first power is 2. We plug in 2, 2 squared is 4, 2 to the third is 8, 2 to the fourth is 16. And you can see it doubles every time we increase the exponent. So where does it start? Well, it starts at x equals 0, y equals 1. So it'd be right here. You know what? Let me pick a different color for this. And you could see that, put a couple of things in here. So when x equals 2, y equals 4. So that would be this dot right here. X equals 1, y equals 2 would be this dot. And you could see it grows really fast, really quickly with regards to, excuse me, the values of x as they, need a drink here real quick. Better. And values of x as it continues to the right are positive values of x. But what happens when we have negative values of x? What happens if this is the case? And I'll leave this in red. Make these all minuses here, right? Well, something that we need to think about is what happens when you have a minus up in the exponent. So what would be 2 to the minus 1? Well, the strategy when you take a look at these minus exponents is this minus implies that it actually flips or puts the numerator as the denominator and vice versa. So you can think about it this way, 1 over 2 to the 1 power. So that would be 1/2. So for example, if I put minus 2 up here, that would be this minus brings the 2 down, and then you square it. So that would be 1 over 4. So I think you see the pattern. So this would be 1 over 8, and this would be 1 over 16, etc., etc. And so when you take a look at this, just put a couple of those in there. And so x equals minus 1, it would be 1/2, and you see we end up with a graph that looks like this. So you could see that in the positive direction, when this base is 2, you could see that it blows up as you go to the right to positive infinity. And what ends up happening when we head to the left on the x? Well, it looks like it's going to get closer and closer and closer to what? The number 0, right? And so if you think about this from our rational function days, that's a horizontal asymptote there with regards to that calculation. And so if I show you on the graph here, or on the slides, excuse me, a prettier looking graph, you can see that's what it looks like. And so as x goes to positive infinity, y blows up really fast. And as x goes to negative infinity, it goes down to zero as the horizontal asymptote. One important attribute to remember is that every exponential function passes through the values x equals 0, y equals 1, because no matter what the base is, anything to the 0 power is 1. So it's interesting, if you change it and make the base a fraction, 1 over 2, for example. And you see that when you do that, it is the complete opposite. And it's the idea that now this will end up blowing up when you go to the negative direction and ends up being positive or going down to 0 in the positive direction. And so what do we mean by that? Well, let me show you just a couple of these real quick, right? So let me just do a couple of these for you. Let's do it in a different color here. Let's see what purple looks like. So say like we had in the purple function, y equals 1/2 to the x power. And say like I said, x equals -1. And so when you plug that in, that would be y equals 1/2 to the -1. And remember what I illustrated in the sense of what that negative means? You flip the base. So the 2 goes on the top, the 1 goes on the bottom, and it would be 1 squared, and it would be 2. So you could see that if I drew it in purple, it's going to go this way, and then in the positive direction, it's going to come down that way. But it'll always pass through that same point, x equals 0, y equals 1. And so we're not going to do too much graphing in this part of the section. We're going to do more of the algebraic manipulation and calculations for these. And so, but I wanted to introduce the general graphs of those functions. And so this is a really nice summary on slide number 9, is where a to the x, where x is any real number, and a is called our base. And every exponential function passes through the graph 0, 1. If a is greater than 1, then as x gets bigger, y gets bigger, and as x gets more negative, it goes to 0. And if it's between 0 and 1 for the base, it does the complete opposite. And so that's what we're going to focus on in this class, is the base being between not 0, right, and not 1, but any other positive number with regards to being greater than 1, which actually blows up in the positive direction, and it being between 0 and 1, which blows up in the negative direction. And so the other base that we are going to introduce that is a super important base is what's called base E, which is called the natural base. And it's amazing how this base shows up in real world modeling a lot. As an engineer, this was the base we used all the time with regards to calculations and modeling. And so, and this actually comes from a crazy looking equation that looks like this. And how do you solve this? Well, if to solve it in a closed form, what you would have to do is a little bit of calculus. I believe it was called L'Hopital's rule. And those of you going into calculus, I think you learned this in Calc 2. And so the idea is that if you don't know, go back to the old guess and check method, right? And how do you do that? Start plugging in values of x to see what you, or n, excuse me, to see what you get. And the idea is, since n is going to positive infinity, you want to plug big values in for x. So what I did here is just made a little table. And as I continue to plug in values for n of 1 and 10 and 1,000 all the way up to, what is that, 1 billion, I think, you can see that it starts to approach the number 2.718 And I believe 2.8 is the next one. And so this is one base that we are going to be using quite a bit in the next few weeks and walking through the rest of this chapter in chapter 6. So one of the other things that you need to get comfortable with is using your calculator and being able to do these calculations using your calculator. Without a calculator, it's going to be really hard to do a lot of the homework and the calculations that we're going to be forming here. So practice. And so you'll see in these slides that there are some examples that you can compare. Each calculator is a little bit different. So I will let you do that kind of on your own time. And if you take a look at these exponential functions, you could see that here we have e to the x or e to the minus x, which are the two opposites, right? And so as you could see that, again, it always passes through 0, 1, but you could see that it behaves the same way with regards to all the graphs that we have done so far. And so that'll end the first of the couple lectures that we're going to do on introduction to exponential functions. This one focused on graphing, and the next ones will focus more on algebraic ways to manipulate exponential